So 5.4 is all about logarithmic functions. So everything that we just talked about with exponential functions, it's just the reverse. Because the definition of a log or log function is the logarithm function is the inverse of an exponential function. So everything that we know about exponentials, we just flip it because we're just switching the domain and the range. So we say a logarithmic function to the base of a, where a is a positive number and a is not equal to 1, is denoted by y equals log base a of x. So we read that as y is the logarithm to the base of a of x. And we say it is defined as log base a of x if and only if x equals a to the y. So the domain of a log function is always positive. And we're going to see that because if you can write logs to exponents, then it makes sense. So if we have y equals log base 3 of x, then that's the same thing as saying 3 to the y equals x. Base, answer, exponent. So we have base, answer, exponent. I'll do that again. If we have 4 equals log base 3 of 81, then base exponent equals answer. So base, answer, exponent. If you can remember base, answer, exponent, that gives you your log setup. Base, answer, exponent. So base, log base 3 of 81 equals our exponent. So logs give us our exponents. So this can be positive or negative. But the number on the inside that we plug in is always positive. And that's because there's no number I can plug in for an exponent that would make my base negative. So again, let's try this. If y equals log base 5 of x, then 5 to the y equals x. Base, answer, exponent. Same thing here. Log base 5, so 5 to the base, answer, exponent. So 5 to the negative first equals 1/5. Base, answer, exponent. This is our log setup. Gives us our base, our exponent, and our answer. So how about changing exponential expressions to logs? Well, if I have 1.2 to the 3 equals m, then this would be log base 1.2 of m equals 3. Base, answer, exponent. Same thing here. I would have log base e of 9 equals b. Base, answer, exponent. Or log base a of 24 equals 4. It's super important that we can go between logs and exponentials and back and forth. And if you remember your bay, then you'll remember base, answer, exponent. So last one, changing log expressions to exponential expressions. Sometimes this is the easier way to solve for things. So we go a base, answer, exponent. Base, answer, exponent. So a to the 5th equals 4. Here we have e to the negative 3rd equals b. Base, answer, exponent. Base, exponent, answer. 3 to the c equals 5. Base, answer, exponent, base, exponent, answer. Okay? So that's our first introduction with logs, is just going back and forth between exponential notation and logarithmic notation. So why is going between these two helpful for us? Well, we can find exact values here, which is evaluating logarithmic expressions. It's saying 2 to some power equals 16. If we switch this to exponential notation. Now, 2 to some power equals 16 would be just solving this, or x equals 4. And that's how we solved exponential functions in the last video. Same thing, log base 3 of 1/27th is the same thing as 3 to some power equals 1 over 27, which is the same thing as 3 to the x equals 3 to the negative third, which x equals negative 3 then. Same thing here, log base e of 1, e to some power equals 1, or what number makes any exponent 0 or 1? X equals 0. So then with the domain of a log function, so remember this is from inverses that we talked about 2 videos ago. The domain of f gives us the range of the inverse, and the range of our function gives us the domain of our inverse. So if you remember what the exponential function looks like graphically, here's, say, e to the x. The domain was all reals, but the range was only positive numbers. So the domain of the log function is the range of the exponential, which is only positive numbers, and the range of the log function, which is the domain of the exponential, is all reals. So in the next box, they summarize some of these properties. Y equals log base a of x, where the domain is anything positive and the range is anything in the real numbers. So find the domain of the logarithmic function. So first off, log base 2 of x plus 3 is just saying what numbers normally can this be? Well, x plus 3 is greater than 0 because whatever I plug in, I want it to be positive. So to solve that, I can plug in anything bigger than negative 3 to get my domain. Likewise, log base 5 of x squared is saying x squared is greater than 0. Well, if you solve this, there's no number that you can plug in for x that would make this, well, besides 0. So x cannot equal 0. Or we can just write x is greater than 0. Now, why do I say that? Well, there are some other properties that we'll see that we still want this to be positive. Last one. Solving all of this, this is our vertical shift. This is just a stretch. So again, we just want the numbers on the inside to be greater than 0. So then we add 5 and divide by 2. Anything bigger than 5/2 will work for our domain. All right, let's flip it. So after we talked about domain, it's assumed that we're going to be talking about graphing. So what's nice is we've already talked about graphing inverse functions, and then we've talked about graphing exponential functions before. So graphing logs is as easy as if we can graph an exponential function, all we have to do is reflect it over the line y equals x. So instead of getting 0, 1, when we plug 0 in for the exponent, we get 1, 0. Instead of 1 comma a, if we plug in a, we get 1 out. So log base a of a is 1. If we plug in 1 over a, we get a negative 1 out, just like we got with exponentials. Now, if we flip it, so this is our function to the negative power, is if we have where x is, this is where x is negative. So I should say A is less than, sorry, A is between 1 and 0, because A's got to be positive. Otherwise, we don't get as much. So here, when it's a fractional, everything is flipped. Now you can see this is our exponential function right here, where it's getting closer and closer to the y-axis. And what we can do is, if you just turned this, then you can see this is just our flipped fractional exponent function. So what should we know about logarithmic graphs? So the domain is the set of positive real numbers. The range is all real numbers. The x-intercept on the graph is 1, and there is no y-intercept. And then the y-axis is now our vertical asymptote, and we're going to be shifting our vertical asymptote. So I always want you to include for log graphs 1, 0, whatever our a value is, and 1 over a, and -1. Now, so that's log base 2, log base 3, log base whatever. If our graph, if our inverse of e to the x, we write this as ln, which is French for logarithm naturel. Sure, that's how you spell naturel. But this is the natural log. That's how we refer to it in English. The natural log is base e. So what the natural log looks like is if we have e to the x as our graph, then this is ln of x. And ln is oftentimes used, other times you see on your calculator it says log, that means base 10. So these are the two graphs that we're going to be working with and shifting around. On the flip side, we have graphs, and then we are done with 5.4. So like I said, we're going to do a couple graphs, and then we're going to be done. I wanted to point this out specifically is if you just see y equals log of x, this is implied base 10. So like on your calculator, if you see just a log, we are assuming to write base 10, but we just drop the 10 because it's simpler to write. And like I said all previous times, mathematicians are inherently lazy and want to find the shortest way to write something. So how do we graph y equals the log of x? So instead of graphing 10 to the x, we're going to be graphing log of x. So if you plug in 1, you get 0 out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you plug in, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I plug in 10, I get 1 out. This is 10, 1. If I plug in 1/10, so if I plug in 1/10, I get -1. And so what this function looks like is it starts growing this way. We have our vertical asymptote on the y-axis, and this is our 10 to the x power, or log base 10 of x. If we have negative ln of x minus 2, that x minus 2 shifts it to the left 2. And this negative is our vertical flip. So instead of going up like this, we're going to be sweeping the other direction. So that means if you plugged in, let's say, 0 or e, you would get 1 out. So e is about 2.7, 1, and then we get -1. And so, likewise, we plugged in 1 over e, we get this, and our graph's going to look like this. We have this is right. And of course, I got to make one mistake at least in every video. This is our flip, and this is right 2, so ignore this. 1, 2. That moves our vertical asymptote 2, and our graph will look like this. Sorry about that. Let's see if I can get one right. So log base 3 of x minus 1. So we are taking log base 3 and moving it down 1. So like I said on the front, the 3 points you need, you should be plugging in 3, 1/3, and 1. Whatever makes that 1. So if I plug in 3 here, log base 3 of 3 is 1. 1 minus 1 is 0. If I plug in 1, I get 0 minus 1, which is negative 1. This is moving down 1. And if I plug in 1/3, I get negative 2, because I get negative 1 minus 1. So our graph, sorry, this is negative 2. This is negative 1. Did not do those in order, and I apologize. Last graph. This would be right 1. So I draw my graph in. The 3 points that I want you to plug in are the base, 1, and 1 over the base. So this should give you 1 out. This will give you 0. And 1/2 will give you negative 1. This is the flip of the exponential functions. So 1, 2, I get 1 out. If I plug in 1, I get 0. And if I plug in 1/2, I get negative 1. Now it takes a little used to getting to graph these, but I think we'll get the hang of it. So try these problems out, and then in class we also have a worksheet that goes with solving.